1 times 10 to the negative 14?
Yeah, we were using that
You don't,
in the S's and bases with the N.
really?
Yeah.
1 times 10 to the negative 14. Now, that's that's logarithms. So if you do logs, then you're going to do, because 10 to the negative 14, that's a pH of 14,
Right.
right?
Yeah.
Which is 1 times 10 to the negative, right? Yeah,
Right.
whatever. So what was your question exactly?
Toward the end of like the mastering chemistry.
Okay, and the homework?
In the homework, with like the video, when we were finding the hydrogen ion concentration, we were taking 1 times 10 to the negative 14th and dividing it over different numbers times 10 to the whatever power to get the hydrogen ion concentration.
Okay, they're probably just going more into logarithm, and we're just keeping it a little less complex. But the hydrogen ion concentration is just, well, it's negative log. No, sorry. So it's 10 to the negative pH, right?
Right.
And basically that's what the logs are.
Yeah. It was just interesting because she used 1 times 10 to the negative 14th.
Oh, Mary did?
Yeah, she
For
did.
all of them.
Yeah.
And then we would divide that by whatever.
One of the pH values that we got. So we'd have 10 to the negative 14th, 1 times 10 to the negative 14th on the numerator, and then the other number
As
on
the
as the denominator.
So what other number?
So, for example, there was sodium hydroxide with a molar concentration of 1.9 times 10 to the negative 2. They want to know the hydrogen ion concentration. And so, to find that, we
Okay.
1 times 10 to the negative 14 divided by 1.9 times 10 to the negative 2 to get our answer, which was 5.3 times 10 to the negative 3.
All right, she's probably just, this is probably the math that you use. So the way I showed you to do it is, so if this is the constant, oh, why not?
I noticed she was doing that, but we did it with a different equation, so I didn't understand that either. But
Okay. So this is the concentration of NaOH, is that right?
Correct.
And so you could find so that's basically the OH concentration, right? Because it's a 1-to-1 ratio.
Yeah.
Okay. And so and we're trying to find the pH, is that what you're trying to find?
You're trying to find the hydrogen ion.
Okay.
concentration, or the
So
polarity.
this is equal to this?
Yeah.
Okay. So if we know this, then we can find the POH, right? No. So yeah, the POH is equal to negative log of the OH, is that right? Log. And then, so once we find the POH, then we could do 14 minus the POH is equal to the pH. And once we have the pH, then we do 10 to the negative pH, and that's going to give our hydrogen ion concentration, right?
Right. And this is
So
how we were doing it in class.
That's kind of a lot of steps, but it's using what we know. And let's see if we can kind of derive this.
Well, the negative log of the OH should tend to.
So if we go, the POH is this. Plug that into here. So 14 minus or plus log of the H plus, and that's the pH. And then it's 10 raised to that power, or the negative of this, is going to be the H plus concentration. And then, oh yeah, this, hold on, this is supposed to be OH, right? So this is the 1.9, let me erase that. This is the 1.92 times 10 to the negative 2, right? So trying to think algebraically how we can. Huh.
So I have an equation that I got where it should put 1 times 10 to the negative 14 equals the concentration of H plus times the concentration of OH minus
Equals H plus times what?
times OH minus. And then she's taking that equation and dividing it
Okay.
to solve for the other one.
Ooh, there you go. Okay, yeah. Huh. But you guys weren't given that one, right?
Yeah, it's not on our,
Yeah.
on our sheet.
Okay.
So
So if you want, you can write that one on your reference sheet, but that would save you some time.
The one that I had written down was the same, except it had KW, which was the constant of,
Water.
I don't even remember.
Yeah.
Well, this has been fun.
Yeah, if you understand the logarithms and all that, there's probably faster ways to go about it, but rather than going through all the logarithm math, then I just kept it to what you guys were given. I don't know. But, yeah, that's right.
Okay.
Good?
Yeah.
All right. Anything else? Okay, we are going to, so chapter 11, last chapter, is about nuclear chemistry. And so before we talk about chemistry, chemical reactions, then what changes in a chemical reaction? Do you remember?
The electrons.
The outside of it, right? Because that's the only part that is affected, in fact, specifically the valence electrons, right? So in a nuclear reaction, what gets changed?
The
The nucleus,
nucleus.
right? Okay. So just a few terms here. So we got nucleons, which are particles of the nucleus. And what are examples of nucleons?
Protons.
Protons and
Neutrons.
neutrons. So we just call those nucleons. And those are the only things that change during a nuclear reaction. Good? So you guys remember what isotopes are? So just a little review. What's an isotope?
positive and negative charged atom.
Not quite, that's an ion. So isotope is an atom of the same element with different number of neutrons. So in other words, they have a different mass number. You remember this stuff back from the very beginning? Okay. And we have a symbol for the isotope as this. You remember this? Where A, that's the mass number, and Z, that's the atomic number, or the number of protons, right? And then this X, that's just the element symbol. Coming back? Okay. So we're going to start using these again. Okay. Because different isotopes behave differently. So, for example, we have what's called radioactive isotopes or radioisotopes. And basically, this is just unstable isotopes. And what part's unstable? The nucleus. Okay. And so if we have an unstable isotope, let's say carbon-14, and then we have carbon-12, which is the majority of carbon, and they're both in a chemical reaction. They have the same properties, same everything. The only difference is this one will react slower because it's heavier. But if it's going to react with oxygen, if carbon reacts with a certain compound, then carbon-14 is also going to react. Okay? Just reacts a little slower because it's heavier. If it's lighter, probably not slower. Good? So let's talk about the difference between nuclear reaction and a chemical reaction. So I think we're pretty familiar with chemical reactions, right? Okay. Okay. So instead of changing the electrons changing, so we already talked about that, the nucleons change, right? Involves the nucleus. Okay, the rate of reaction is unchanged with increase in temperature, if you increase surface area, all the things that will change the rate of reaction for a chemical reaction, that doesn't affect nuclear reactions. So the rate of reaction is unchanged. That makes sense? So if we, you guys, I don't know if you remember doing it in lab, if you want to speed up the reaction, what do? You heat it up. You stir it. You do something to it, right? And those things, you can do that to the nucleus of an atom will not change. Okay? Even though the nuclear reaction has a consistent rate, you can't speed it up, you can't slow it down, it just continues to react. And why does it react? Because you have an unstable isotope, a radioisotope, that will decay or react in the nucleus until it becomes stable. Not necessarily that one, but it will become a stable isotope. And it'll continue to decay, continue to react until it's stable. Good? So let's just write that for the next part. Nucleus will react regardless of what's happening. Or of its surroundings. Good? And the last part is nuclear reactions will give off much, much, much more energy than chemical reactions. Any questions about the difference between nuclear and chemical reactions? No? All right. So let's first discuss, next let's discuss the different particles that come off of the nucleus during these nuclear reactions. So I'm going to just make a little table here. So we got the particle, mass of the particle, charge of the particle, and I would memorize this stuff. You need to know it. Either that or put it on your reference sheet. I don't know how much room you'll have on it, but charge, location, and symbol. Okay, the first particle we're going to talk about is a beta particle. And a beta particle has a mass of 0. What else has a mass of 0? Electrons. That's because a beta particle is an electron. So what's its charge? -1, right? And where is it located? Inside the nucleus. Whoa, whoa. Not wild? So we don't call this an electron because it's inside the nucleus. We call it a beta particle. Why? Because beta is after alpha. We're going to talk about alpha particle too. Okay? And the symbol we use is the symbol of an electron. Has a mass of 0, charge of -1, and its symbol is E. So when we deal with beta decay or beta emission, then we have to know what that is so that we can know what the product will be. Good? And if it sounds scary, if you know these symbols, it's actually easier than chemical reactions, okay? Yeah.
Why is the charge for this one on the bottom?
Oh, good. Ask that in just a minute.
Okay.
Okay? So next, let's do alpha particle. Alpha particle has a mass of 4, a charge of positive 2, and it also comes from the nucleus. And its symbol is 4,2He. Yeah, it's the helium nucleus. What's the charge of a helium nucleus? Positive 2. Hence, that number right there is a positive 2. This number right here is a negative 1. It doesn't have, so we normally refer that to as the atomic number, right? Okay, and that's still the atomic number. But if we have a negative 1 down there, does that mean it has negative 1 protons? We just call it its charge. Good? Questions so far? This is just fact stuff, right? Okay, and you guys know what a proton, electron, and neutron symbol is, right? And when we talk about it in terms of nuclear reactions, so if we talk about a proton,
The hydrogen.
mass of 1, charge of positive 1, it's in the nucleus. This is a 1,1p, right? Mass of 1, it is 1 proton. And if we do neutrons, has a mass of 1, charge of 0. It's also in the nucleus. 10N, right? Y'all understand this notation? Any questions? Okay, we got a positron. Now it sounds like we're just making up names, right? A positron is basically a positively charged electron. So if we write the symbol, it is 0, positive 1e. Okay? So its mass is 0, charge is positive 1, and it also comes from the nucleus. So if you learn, I took a class called nuclear particle physics. There's a lot more particles in the nucleus than just 2. Okay? We're not going to talk about all of them, but these will come out of the nucleus, and we'll talk about what happens and what the products are. And the last one is a gamma ray. Not a particle, but a ray. Has a mass of 0, a charge of 0, and it also comes from the nucleus. And its symbol is a Greek letter gamma. And if we want to write the mass is 0, charge is 0, that's what it would look like. And basically, gamma is what? It's the stuff that makes your skin green and pants purple, right? No, I'm just kidding. It's light. That's what it is. Yeah, it's radiation. It's the highest energy of electromagnetic radiation, which the next highest is X-ray, ultraviolet, then visible light, infrared, microwave, and radio. All of those are electromagnetic radiation, and gamma is just the highest energy form of that. So all of that, they travel the speed of light. They're all light. The only one that we call light is the one that we can see, right? Good? Any questions on those? So get that down. Try to have them stuck in your brain. All right, now let's talk about the different types of nuclear reactions. Ready to move on? Do you need to write this still? Good. All right, let's start with alpha emission. Sometimes called alpha decay. What does decay mean? Breaking down, right? Emission, what does emission mean? It's coming off, right? And it's actually being shot out of the nucleus of an atom. And when alpha emission occurs, an alpha particle is being emitted out of the nucleus. Yeah? So let's do an example of this. You have uranium-238, for example. So remember, that's just the mass number of uranium, right? So sometimes it calls uranium-238 like this. Uranium-238. That's how we read it. The isotope symbol we write like this. Why is there a 92 right there? Because that's the atomic number of uranium, right? You all remember this stuff? Okay. And then we draw this arrow just like in our chemical reaction, but this is a nuclear reaction, and it emits an alpha particle. What's the alpha particle? It's the nucleus of a helium atom, right? And the symbol is 4,2He, right? So this is the helium atom without the electrons. Good? And this is actually the thing that Ernest Rutherford experimented with his gold foil experiment. Remember that? And he shot it at this gold foil, and most of them went through. Okay? Anyway. What are we left with? This will be a good test question. What is the product? Thorium? How do you know?
2 plus 90 is 90.
Yeah. We have a mass of 238, and we can write an equation. If you guys like equations, because it's math, just write it out, and it gives you right every single time if you understand algebra, right? So we can write 238, and this is like our equal sign, right? Equals, and we're just dealing with the top number first, one step at a time, is equal to 4 plus, and then we can call this AZX, right? This is our isotope we're looking for. And so then we add the A. And then we can solve for A by subtracting 4 to both sides. And we got A is equal to 234. So our compound is going to have a 234 on top. Y'all with me? And then we could do the same thing with this bottom number. 92 is equal to 2 plus Z. And then we subtract 2 to both sides, and we got Z is equal to 90. So that number down here on the bottom is 90. That's our atomic number, so we look on the periodic table, and it tells us 90 is thorium. Good. Do we get that? Questions? Right? And yeah, there's a way to check this, guys, and you should check this. so this is 234, thorium-234. 234 plus 4, is that equal to 238? Yes. Double check it. 90 plus 2, is that equal to 92? Yes. Easy to check. Okay? And do you have to write the equation? No, you don't. But the part where people make mistakes, where I find the most mistakes, is when we do beta decay. And I'll show you when we get there. It's the same, mathematics is still the same. So if you write the equation, you'll know what to do if you understand basic algebra, right? But anyway, I'll show you why people make that mistake. Anyway, here we go. Does that make sense, guys? You want to do another one? Yeah, let's do another one. All right, so let's do polonium-208. And it undergoes alpha decay or alpha emission. Go ahead and figure out what isotope we're left with. Yeah, you'll need a periodic table. Anybody have this one yet? What do we got?
Lead 204 for the 6.
Lead 204. Good.
And 82.
Good. Now, why does this happen? Because this guy is unstable. It's a radioisotope. And it's going to do what it needs to do to become more stable. And it's going to do this until it becomes stable. So what makes it unstable? Any ideas? You have the nucleus. What's inside the nucleus? Protons, right? And neutrons, but protons. Protons are positively charged. What happens to two positively charged particles when they come together? They repel. What? All of these protons are tightly packed. How? What? What's going on? It turns out there's a force that's stronger than the electrostatic force. The electrostatic force causes them to repel, right? But if they get close enough, if there's enough energy to push them together, they will hold together a lot harder than being pushed apart. And that's called the nuclear strong force. But anyway, so these guys are together, but the electrostatic force wants to push them apart. And that's what makes them unstable. Okay? So what holds them in? Neutrons. Neutrons act as nuclear glue. And so if you look at the periodic table, the very first ones, the lightest ones, how many protons do we have compared to how many neutrons do we have? Let's look at oxygen. How many protons does oxygen have? 16. No.
No, 8.
8, because that's the atomic number, right? How many neutrons does it have?
Also
8. You remember this, guys? We have, let's do this. Oxygen, so the atomic mass of oxygen is basically 16, right? So it looks like this. And do you remember how to calculate the number of neutrons? Remember doing this? The mass number subtract the atomic number, that gives us the number of neutrons. Remember this? We're going to have to do this again. Okay, so write that down. So we can even write an equation if you'd like. Neutrons equals mass number minus the atomic number. Or if you just remember doing that, we're good. Okay. So it has 8 neutrons to 8 protons. 1-to-1 ratio, yeah? Let's go to calcium. What's the ratio of neutrons to protons for calcium?
It's about a 2-to-1.
Try again. Calcium is 40-20, right? How many neutrons does it have? 20. 40 minus 20 is 20. And it has 20 protons. A 1-to-1 ratio, right? So the lighter elements have near a 1-to-1 ratio. Right? Almost exactly, not all of them, but... And then what happens as you get to uranium, or let's say polonium? How many neutrons does polonium-208 have? (208) subtract 84,
125.
125, and how many protons? 84, right? That's a lot more than a 1-to-1 ratio now. So what's going on? Why do they need more neutrons the heavier it gets?
Because this,
More protons, you got to have more glue to hold them together. And as they get heavier and heavier and heavier, they become more unstable. So anything past 83, atomic number 83, will undergo alpha decay. Why? What happens in alpha decay? We lose 2 protons and 2 neutrons. Because that's what an alpha particle is. 2 protons and 2 neutrons. Do you see that? Oh, yeah. Okay. So an isotope that undergoes alpha decay is because it has too many protons. So anything higher than 83 will undergo alpha decay. I'm not saying if it's under 83 it will not, but if it has too many protons, it's going to do something to get rid of them. It's like, oh man, you guys we hate each other. They're pushing apart. So it pops out an alpha particle. Does that make sense? Okay. So we can say alpha emission occurs when there are too many protons. We can say, note all above atomic number 83 will undergo alpha decay or alpha emission. Because we have way too many protons, right? We good there? All right. Let's do beta emission next, unless you have any questions. Also could be called beta decay, where the nucleus decays a beta particle, right? And let me show you what goes on in the nucleus for beta decay. For alpha decay, you just get 2 protons and 2 neutrons that just pop off, right? That seems reasonable understanding, right? Maybe? Yes? No? Okay. So for beta emission, what's happening is we have a neutron in the nucleus. It shoots off an electron or a beta particle. And what's left? Let's do the math. You start with 1. We get rid of a mass of 0. What are we left with? 1, right? We start with a charge of 0 or 0 protons, charge of 0. We get rid of a negative charge. What's 0 minus a negative? 0 minus a negative 1 is? Positive 1, right? So that neutron, by getting rid of the beta particle, turns into a proton. So when does beta emission occur? When not enough protons compared to neutrons, right? So it's kind of like the opposite of beta, or alpha. Kind of ish, not really, but I wouldn't say that. Or you might say it doesn't have enough neutrons, or no, it has too many neutrons, right? Either way. So let's do another one. And you guys some of you made the same mistake that many students do when we did this one. But let's do another one, see if we can not make a mistake here. So let's do with iodine 131. And it undergoes beta decay. What are we left with? If you write down the equation, you'll get it right every time, unless you don't understand basic algebra. 131 equals 0 plus something, right? We could subtract 0. Oh, that doesn't do anything. It's just 131, right? That's not the hard part. We don't even have to do an equation there, right? If we go 53 is equal to negative 1 plus x. What do we do to solve for x? We add 1. And it's 53. Sorry, it's 54. I made the mistake, didn't I? No. So most students will say 52. Because they'll say, oh, just like over here, we did 84 minus 2 is 82, right? Now come over here, 53 minus 1 is 52. But it's not minus 1, it's minus a minus 1. You with me? So just keep that in mind. So what isotope is this? Xenon. Pretty straightforward. Is this easier than acid bases? Okay, good. Let's do one more. Carbon 14 undergoes beta decay. Go. I know I didn't write everything down. If you understand this, you should be able to finish it. So carbon 14 undergoes beta decay. If you don't understand it, that's okay, we'll get you there. Just try it. You will need to use your periodic table though. How are we feeling? Got this? Okay, so what number goes down here, guys?
6.
Yeah, because it's carbon, right? And what's a beta particle? 0, -1 e. So we got to know that, right? And then we could do the math. So what number goes on top? What's the mass number of our isotope? 14. And what's the bottom number? 7. And you can check 7 plus -1, is that 6? Yeah, always double check it, especially on beta. And what element is this? Nitrogen. Good? Questions on beta emission and alpha emission? Pretty straightforward? Okay. Let's do 2 more decays. The next one is positron emission. So remember, emission means it's coming out of the nucleus, right? So positron emission, we're getting rid of a positron, which is a positive electron, right? So what happens here? We have a proton that gets rid of an electron, not an electron, sorry, a positron, and what's left? What is that? Why is a mass of 1, charge of 0? A neutron. So it's when a proton turns into a neutron. This is the exact opposite of beta emission, right? So when does positron emission happen?
When a proton turns into a neutron.
When you don't have enough neutrons. So we turn a proton into a neutron. And that's what makes it more stable. Good? So really we're looking at the ratio of neutrons to protons. If it's close to 1, it's going to be more stable. Farther from 1, less stable. Good? So let's do an example here. Potassium 40 undergoes positron emission. Positron. Keep doing that. When you have it, tell me what the product is. Can we do this without my help right now? Are we good? It's the same math no matter what we're dealing with. So we just have to know the different particles so we know what to write, yeah? Okay, what do we get? Calcium 40? Is that what we get? Let's check. Does 20 plus 1 equals 19? No. No, it doesn't. So this is 40. That's true. What's this bottom number? Has to be 18, because 18 plus 1 is equal to 19. Double check that. It's easy to make a mistake if we just do it in our head. How many of you did it in your head? Just saying.
When you wrote down calcium, I was like, wait a minute.
Okay. So show your work. Make your mistakes here, not on the exam, right? Okay. Are we good? Do you want to do another, or do you want to move on? Moving on? Okay. So the next one is electron capture. In electron capture, this electron is actually coming from the electron cloud outside the nucleus. And sometimes it'll take one in to make it more stable. So, for example, we have mercury 197, and it's an electron capture, so we're taking it in before the arrow. And it's an electron. It looks just like a beta particle, right? And we want to know what we end with. So 197 plus 0 is equal to 197. 80 plus a negative 1 is equal to 79. Gold. Woo! Yeah, we know how to make gold now. Wait. Okay. Can you do that? Can you speed up this reaction? No. And is it always gonna? So it's just gonna keep going until it becomes stable. Could take a minute to become stable. Could take years to become stable. So depending on which isotope it is. Okay. Good enough? Let's do one more. Arsenic 73. What are we left with? This one's a little easier to do in your head because it's already set up, right? What's the top number?
73,
What's the bottom number?
32,
What's the element?
germanium.
Good? Well, I wish chemistry was all this way, right? It's like, oh, I could do this. All right. Let me see here. So do you want to practice some of this on the worksheet? So section 1 just tells you to determine the number of protons and neutrons that are found in each isotope and how many total nucleons there are. Should we do the first one together? Make sure we understand what's going on. Okay, so plutonium 244 has how many protons? 94, because that's its bottom number. Y'all with me? How many neutrons? How do we figure it out? 244 subtract 94, and what do we get?
150,
150 neutrons. And how many nucleons?
244.
Yeah, just this number right here, right? Because remember, the mass number is protons plus neutrons. Simple enough? So ladies and gents, this is for your practice. If you got it, move on to the next stuff. Okay. Go ahead and practice that. How are we feeling? Good? So, that's half of the lesson. We can keep going, try to finish this, or we can be done and finish the rest next time. What do you guys want? At least do a little bit more? Okay. All right. The next three are, so these are like, well, I guess electron capture is one of these. So the first two, alpha, so the first three, alpha emission, beta emission, and positron emission, that's where we're getting rid of stuff, right? Electron capture is one of the four that is considered nuclear reaction. So the next nuclear reaction is nuclear fission. Have you ever heard of nuclear energy? This is where we get nuclear energy, from nuclear fission. And nuclear fission is when a larger isotope breaks down, oops, into smaller isotopes, smaller nuclei. So it splits it, right? And so here's the reaction, a fission reaction. An example is uranium-235 is a fissionable isotope. Not all isotopes will undergo fission. And how you break it apart is you chuck a neutron at it. Oops. And then it splits into two smaller isotopes. And more neutrons. So if we draw this little cartoon here, we got this uranium isotope that is fired upon by this high-speed neutron. It splits into two smaller isotopes. And some more neutrons. Exactly 3? Not necessarily, but more neutrons, right? And then what do those neutrons do? It was kind of like an explosion. They're going faster. What happens? Yeah, there's more uraniums around. So there's plenty of uraniums around. So these are all uraniums. And these guys strike that, and they split again. Whoops. And it just keeps going that way. And we call this the nuclear chain reaction. When this happens, we get a lot of energy. Okay? I might have given you too much information, but are we good there? So let's see if we can do a problem like this.
Well, how did you know which ones it broke into?
Good question. Here, we're going to do that right now. Okay? And really how you know is you actually do it. Right? Okay? But we're not going to do this in lab, okay?
Nuclear fission.
Okay, can you guys figure out what the missing isotope is? So I will never have you figure out both of them, because you can't without actually doing this, but the math is all the same. It's a lot easier to write an equation for these because there's a lot more involved. Should we do it? So we start with 235, and I'll just do the top number first. Plus a 1 is equal to some number, we don't know what it is. plus 137 plus what? We have 2 neutrons. Each of them have a mass of 1, so that's a total of 2. You with me? Okay. And this is 139, so we subtract 139 to both sides. Whoops. Subtract 139. So 236 minus 139 gives us 97. Then we do the same thing. The bottom numbers, 92 plus 0 equals something plus 52 plus 0 again. You following? Am I going too quickly? So we just subtract 52 to both sides, and we get 40. Okay? So it's just a little bit more complex, but not too bad, right? What do you think? All right, that's fission. And fusion, where does fusion occur? In the stars, in the sun. Okay? Well, so far, we haven't figured out how to sustain fusion, except for Dr. Octopus. He did. You guys know? Okay, whatever. Okay. So fusion is the opposite of fission, and it's when 2 smaller nuclei fuse together to form a larger nucleus. And the reason why it has to be done in the stars, because there's enough energy to get it to fuse. So we have, for example, 2 protons, or two hydrogen atoms, because that's what most of the sun is made of, is hydrogen. So we have 2 hydrogen atoms. For example, 2 different isotopes of hydrogen. If these guys come together, hydrogen is basically a proton, right? If these guys come together, what's going to happen? They're going to repel. So if it's hot enough, enough energy to push them together, and as soon as they get close enough, that nuclear strong force comes in and holds them together. And then, now it's what? Helium, right? So in this case, 5,2-He, but just a different isotope of helium. Make sense? Now, the examples, I don't know if you'll be given these examples on, that's okay. I'm not going to be technical about this. I'm just going to give you some more examples. They might not be real, but we'll just give them to you, okay? That's really, so you can take heavier isotopes like hydrogen or helium and another hydrogen. What are you going to get? Lithium, right? Maybe two heliums, and you're going to get something heavier. What's that? Beryllium, and so on, right? So that's how all of the heavier elements up to iron are created. And then what about after that? Then we got supernovas, and we got when you get more energy, you can get. We're not going to go real in depth. Is that okay? Unless you really want to know. I like this stuff, so I could tell you, but I'm not going to test you on this. So your call. All right, so let's do another example. Silver 109 plus helium. And again, this is not real. I don't know why this example is even in here, but it's not real. But that's okay. We can still do the math, right? When things come together, this is called fusion. When it breaks apart, called fission. So what are we left with? What? Indium? Let's find out. So we got 109 plus 4 is 113. 47 plus 2 is 49. And what's 49? Is it? Okay, maybe I have it written wrong here. What's the symbol for indium? IN? I have a mistake in my notes then. Yep, sure do. Okay. That's okay. Good enough? All right. Okay, gamma radiation. When does gamma occur? So if we have, let's say, uranium-238, for example, and gamma particle is just, or gamma ray is just that, right? What are we left with?
Uranium.
Nothing happens, right? So does this happen by itself? No, it doesn't, because it doesn't make it more stable, right? So it doesn't really change anything. So what really happens is we might undergo beta decay, for example, plus gamma radiation. So this just spits off extra energy coming off, yeah? That's usually when it happens. And then we can just kind of ignore this right there. And we end up with 238 and 93, right? And 93 is Neptunium. Good? So just know that gamma radiation doesn't come off by itself. And one other thing you need to know, the 3 types of nuclear radiation. We got alpha, beta, and gamma. 3 letters of the alphabet. Greek alphabet, right? This one has highest penetrating power. What does it mean to penetrate? Go into something else, right? And this one is the lowest penetrating power. Can you make sense of that? Yes or no? Why would gamma be the highest and why would alpha be the lowest?
Because Hulk is the strongest of it.
Yeah, no. You got some people that are going against you now.
I'm just kidding.
No, really, why?
Gamma ray smaller.
Gamma's the smallest, and alpha's the largest. So the medium penetrating power would be beta, right? So gamma can go through lead. It's stopped a little bit by lead, kind of like X-ray is stopped by lead, right? X-ray is not quite as much energy as gamma. Beta can go through thin metals like aluminum foil, and alpha is stopped by paper, thin paper, okay? Any questions on everything so far? How you feeling? You want to tackle the last thing? This is the hardest part of today. It's more mathy. Okay, it's not really that difficult once you learn the process. How you feeling? You want your call? You want to go? All right, let's do it. Well, on the worksheet, we could do section 3. So section 2 says, say what type of emission is occurring. So alpha, beta, or electron or positron emission, right? And then section 3, we're dealing with the different types of nuclear reactions. So that's electron capture, fission, fusion, and gamma. Good? You want to practice some of that or just move on? Your call.
Move on.
I'm hearing moving on. What are you guys feeling? Okay. All right. So let's do half-life. Half-life is the time it takes for half of an unstable isotope or a radioisotope to decay into another isotope. And ladies and gents, this is just probability, like flipping a coin. You're going to get heads 50% of the time? If you flip a coin? No. You might on occasion, but it's not going to be exactly 50%, right? So half-life is, we say half, but is it exactly half? No, it's not. But this is a good prediction, is all, okay? So, one half-life well, that's just half of what we start with, right? If we have 2 half-lives, then that's a half times a half, which equals 1/4 of what we started with. You with me? So it doesn't go half and then just take the rest of it. It's half and then half of what you're left with, half of what you're left with, and so on. So you actually, if you follow that, you'll never get there, right? But will we? Yes, we will, okay? Because it's just a probability. So 3 half-lives is going to be what?
Half times half times half.
Half times half times half. Or 1/8, right? We good? So that's the math. Can you handle the math? Okay. Let's do an example. Kind of that's all the math is. So let's say we have strontium-90. And strontium-90 has a half-life, I could just abbreviate it T sub 1/2, of 28.8 years. So that means after 28.8 years, we're going to have half of what we started with. You follow?
Sorry, that's T 1/2?
Yeah, that's, you don't have to do it that way, but that's a good symbol. Half-life, the time it takes for half of it to decay, okay? If we start with the 5-gram sample of strontium-90, how much will be left after a time of 85 years? Okay, ladies and gents, you take Math 1050, anybody? Okay, there's an equation you can use, but it's icky, icky, yucky. We can just throw out that equation and keep it simple. Should we do that? Okay, now, if we're doing hundreds of half-lives, yeah, we'll want to refer to that equation. But in this class, we're not going to do hundreds. Maximum below 10. Okay? So here we go. Here's how I do it. You don't have to choose to do it the way I do it. I say times 0, when there's 0 half-lives into it, that's what we start with. Starting amount. You with me? So that's when I first start the stopwatch. That's how much I start with, right? And then after 1 half-life, we have half as much, right? So in other words, we times this by 1/2, or divide by 2. You following? And then after 2 half-lives, we times whatever we get here by 1/2, and so on. You follow? Now the question is, how do we determine how many times we divide by 2? Well, let's see. If we have 85 years goes by, how many half-lives is that? Can you figure that out? 3? How did you figure that out? 85 divided by 28.2. Does that make sense, guys? 3 half-lives fit into 85 years. And it's always going to be a perfect, nice number, guys. We're going to keep it simple. So let's start this problem. So at time 0, how much do we have? 5 grams. And we just figured out 85 divided by 28.8. So in other words, the time divided by our half-life is equal to the number of half-lives, right? And we figured that to be 3. Is that right? Yeah, okay. So we're going to just cut this in half 3 times. So after 28.8 years, or 1 half-life, how much do we have? 2.5 grams. And is it going to be exactly 2.5, guys? No, we're just making predictions here. Okay. After 2 half-lives, 1.25, and we got to go 3 half-lives to be 0.625 grams. That's how much we have after 85 years. Make sense? Anybody want a formula? Okay, here we go. The amount remaining is equal to the original amount multiplied by 1/2 raised to y. We can call y equal the number of half-lives. I know that's a little bit simpler than the Math 1050 one, but so if you want to use that, you can. But I find it's, I mean, we're gonna just do 3 or 5 half-lives. It's just divide by 2, right? Is that all it's gonna be? Not quite. But that's the basic process. For example, I might give you this and tell you to find this. And I'm still going to give you, after 85 years, and our half-life is 28.8, still 3 half-lives. How do we go backwards? Oh, we multiply by 2 until we're done with our number of half-lives. Make sense? Or maybe instead I'll say, well, how much time has elapsed if I give you this and give you this? We can figure out how many half-lives it takes to get there. Times that by the half-life, and that's how much time has elapsed. Does that make sense? Oh, what if I says, what is the half-life? If I know this, and I know this, and I know the time, I can again figure out how many half-lives, find the total time divided by the number of half-lives, and that's going to be our half-life. Make sense? It might make more sense if we do more problems, yeah? But those are the only options I can ask you. So let's do some. So on the back page of your worksheet, it says calculate the following quantities. So gold 198 has a half-life, so T 1/2 of about 2.67 days. We start with a 14.5 nanogram sample. How do you know it starts? Because then it says how much is left after a time of 8 days, right? How much is left over? So this is just like the one we did, right? Do you want to try it by yourself? Try it. I start with how much I start with. That's how I start it. And then I figure out how many half-lives, and I go from there. Got it? Not yet. Keep going. So what do we start with, guys? 14.5 nanograms. How many half-lives are we going to deal with? So 8 divided by 2.67. So I'm going to just count 1, 2, 3. So we're going to divide it by 2, 3 times. So that's going to be 7.25, is it? Then a half again is 3.625. Then half again. Done. Good enough? Easy? Hard? Okay. So much easier than stoichiometry. Okay. All right, so you want to do the next one? Do you want to work on these together, or do you want to try them?
Try it.
Can we try one with the equation?
Yeah, together? All right, yeah, let's do it. So thallium-208 has a half-life of 3.053 minutes. How long will it take a 120-gram sample to decay all the way to 7.5 grams? So how long? Okay, so we know how much we end with, right? 7.5 grams. So if we use this equation, is equal to how much we start with, 120 grams. I'm going to just leave these numbers out, or sorry, the units out, just to keep it a little simpler, okay? Times 1/2 raised to the number of half-lives. X, right? That's the only thing we don't know. This one's a little bit harder using the formula without logarithms. This is why I don't use that. I never use it for these simple problems, okay? So I'm going to just, after 1 half-life, how much do I have left? 60, right? After 2 half-lives, we have 30. After 3 half-lives, we have 15, and after 4 we have 7.5. So 4 half-lives, and each half-life is 3.053 minutes. So how much time has gone by? 4 multiply our half-lives. You with me? What is that?
12.2.
12.2 minutes. 12 point what?
12.212.
Okay, that's good enough. Does that make sense, guys? Should you do the next one? Or do you want to try? I don't want to take all your practice away. But at the same time, I want to make sure you can see all the different types. Let's see. The next one says how much of the iodine was originally present. So this is a different one. Should we try it together? So the half-life of iodine 131 is 8.1 days. Wants to know how much do we have originally, so that's what we're looking for. If we have 6.25 grams left after a time of 24.3 days. So what's our first step? Find out how many half-lives. Because we have both times, so 24.3 divided 8.10 is 3 half-lives, right? That means after our third half-life, we have 6.25. How much do we have after our second half-life? What do we do? Multiply by 2. Instead of divide, because we're going the other way, multiply by 2, we got 12.5. With me? After 1 half-life, how much do we have? 25. And so our original amount is 50 grams. Pretty straightforward, or no? And the next one, well, the next two don't have anything to do with half-life. I don't know why they're even on there. That's it. Any questions? Well, it's a good thing we end on a high note then, huh? All right, well, have a fantastic Thanksgiving, ladies and gents, and be safe out there.